A disk of mass m slides from rest on an inclined plane. The angle of inclination is given as alpha. The problem says it travels a distance L before it stops. We're asked to find the work done by the friction forces. So let's take a look at the picture. So that's the incline, and then it leads into a horizontal plane. Suppose the disk starts from here with 0 speed, and then it stops somewhere here. The final velocity is 0. The angle of inclination is alpha. If I consider the length of the incline projected horizontally, if I take that as x, the length of the incline would be, so that would be, we can take that as x by cos alpha, and the height is x tan alpha. Okay, now let's split the entire path. Let's say it starts at a point A. Once it reaches the bottom of the incline, let's say this is B, and then the final point is C. Now it is starting from rest and then it ends at rest. So the change in kinetic energy is 0. So here we can again use the work energy theorem to get the work done by friction. So if I write down the work energy theorem, there are two forces, one friction and the other is gravitational force. So work done by gravity plus work done by friction, I'll split this along the path. So let's say along section AB plus work done by friction along section BC is change in kinetic energy, which is anyway 0. Now the gravitational force is pointing in the downward direction. The displacement till it hits the horizontal level is x tan alpha. So here we can say the work done by gravitational force is mg multiplied by the displacement, which is x tan alpha. Plus we need to get the work done by friction. Now if I consider the incline, while the disk is on the incline, if you look at the free body diagram, the normal force is in this direction, mg is in this direction. Okay, so if I take the component of the gravitational force, this is alpha, so the component is mg cos alpha. So the normal force is mg, so I'll write it here, normal force is mg cos alpha. Because the disk is sliding, the friction force while it is on the incline, let's say I'll write as FAB, is mu times normal, which is mu mg cos alpha. But when the block reaches the horizontal level, in this case the normal reaction is mg. So from B to C, the friction force is mu mg. Okay, so you need to note this difference, and then BC is given as L. Okay, so if I write down the work done by friction from A to B, the work done by friction is obviously negative, so minus the frictional force is mu mg cos alpha, and the displacement is x by cos alpha. Okay, so sorry for this clutter here. So this is the force right here, and x by cos alpha is the displacement on the incline. And work done by friction from B to C is again minus mu mg into L. Now this entire thing is anyway 0. So from here, the unknown that we are after is x. Once we get x, I think we can find the work done, which is this part, this portion. Okay, so how do I get x here? I think in each of the terms, mg is common, and then right hand side is 0. So I can ignore mg, and then here cos alpha disappears. So I have x tan alpha minus mu x minus mu L is 0. So from here we get x as mu L by tan alpha minus mu. Okay, so that is the projected length of the incline horizontally. Okay, so now if I look at the work done by friction, all I have to do is I'll have to consider this part, okay, and then just substitute x here. Okay, so let's do that here. Okay, so work done by friction is obviously negative. So here I can take it is minus mg is anyway common, mu mg, so I'll pull that out, and I have x and then I have L. So I have to take x plus L. Okay, so here if you substitute this, so what is x plus L? So if I add L on either side, suppose, okay, suppose if I add L here, what do I get? So I have minus mu mg, and then if I add L, I think mu L will disappear, so I should get L into tan alpha, and in the denominator you have tan alpha minus mu g. So I think the answer expected by the author is in terms of cot. So all we can do here is just divide the numerator and denominator by tan alpha, so you will end up having minus mu g L upon 1 minus mu by tan alpha, which I can write it as cot alpha. Okay, so that's the answer.